So, last class I have discussed that how we can develop load settlement curve for pile analytically based on elastic analysis. Now, this is the procedure that I have discussed, and these are the curves. So, as I have discussed that first the friction resistance will be mobilized, then the tip resistance will be mobilized, and during the friction resistance mobilization there will be also some amount of the tip resistance. So, this curve is the curve for friction resistance or shaft load versus settlement, this curve, and there is this red curve is for the tip resistance versus settlement, and this blue curve is the overall load settlement behavior, that means the shaft load plus tip load versus settlement. And then I have drawn a blue dotted line. So, as I mentioned that actually the tip load versus settlement, that means settlement of the soil due to the tip load is representing by this blue curve, blue dotted line. Okay. And this additional portion of the settlement, because this is x axis the settlement. So, additional portion of the settlement is due to the settlement of the pile or pile material, and that will happen due to the tip load. Okay. And again, as I have already mentioned that this compression of the pile material will take place once the compression of the soil will be over. Okay. So, that means once the compression of the soil will be over due to the tip resistance or tip load, then only the compression of the pile will take place, unless there is a complete there is a slip between the soil and the pile, or there is a settlement of the pile due to the deformation of the soil. During that moment, the deformation of the pile material will not take place. So, deformation of the pile material will take place once the deformation of the pile material is over. Okay. So, that means we can say this up to this blue line, this is the deformation of the soil due to the tip load. Then once it is done, then the deformation of the pile material will take place, and then the overall deformation of the pile material plus soil due to the tip load is this red line. So, that means the overall load settlement curve will be the deformation of the soil due to the shaft load plus deformation of the soil due to the tip load plus deformation of the pile material. So, these three summation of these three components will give us the overall load settlement curve. And that means, as I mentioned, when the shaft resistance is fully mobilized, during that time also there will be some tip resistance or tip load, this amount, small amount, but that tip load will not contribute during the compression of the pile material. So, when you calculate or when we calculate the compression of the pile material, so that portion of the tip resistance we have to subtract, okay, from the overall tip load. Okay. So, overall tip load will give us the deformation of the soil due to the tip resistance or tip load, but when you calculate the deformation of the pile material, then you have to subtract that portion of the tip load which is developed during the full mobilization of the shaft resistance or friction resistance. So, this is this amount. So, that is done, and then we should know the values of these four quantities, then only we can draw this overall curve or the other curves also. So, and I have given how we can determine these four quantities. So, now today I will solve one example problem. So, that example problem is is that we have a pile whose elastic modulus of the pile material is 20 into 10 to the power 6 kilonewton per meter square. Elastic modulus of the soil is 70 into 10 to the power 3 kilonewton per meter square. Average undrained cohesion is 100 kilonewton per meter square, that is average along the pile shaft, that means along the length of the pile, and cohesion at the base is 120 kilonewton per meter square. Then mu value of the soil is 0.5, it is a cohesive soil. Then alpha adhesion factor is 0.35. So, I have already given you the table from where you can determine the adhesion factor for different soil or different cohesive value of the soil. And so, adhesion is alpha into cohesion. Okay. So, now the it is a circular pile whose diameter is 0.5 meter and length of the pile is 15 meter. It is in floating pile and we have taken the average cohesion. So, that means it is a floating pile. So, now the portion of the load that will transfer to the tip, that is equal to beta 0 C k and C nu. So, what is beta 0, what is C k, what is C nu, that I have discussed. So, now we have d b, that means the diameter of the base and the diameter of the shaft. So, both are same because it is a uniform cross section. So, that means we can write this is equal to 1 and L by D is 15 minus 0.5. So, that is equal to 30. Okay. So, now if I go to that chart. So, the L by D is equal to 30 and dB by B is equal to 1. So, this is 31, this is the value. So, beta 0 value will be 0.05. So, this is 0.04, 0.05, 0.06. So, that means beta 0 value corresponding to L by D is equal to 30 and dB by B equal to 1, because this is dB by B equal to 1, this is 2, this is 3. So, this value is beta 0 is 0.35. Then we have two correction factors. One is the correction factor for mu Poisson ratio. So, that we have to take in as 1, because these beta 0 is developed for Poisson ratio equal to 0.5 and our soil Poisson ratio is also 0.5. So, no correction is required. So, we have to take in the C nu is equal to 1, because for 0.5 this value is 1. Now, we have to take the value of C v. So, now we can write that here corresponding to this value we have taken beta 0 equal to 0.5 or 0.05. Okay. Now, we know that our k value is E p R a. So, what is k I have discussed? E s. This is the k value and E p is 2 into 10 to the power 6 and it is a solid pile, solid cross section or solid pile. So, that means the R a will be 1. So, R a will be 1. So, I have already discussed in the last class how we can determine the R a for solid pile or for the hollow pile. So, it is for solid pile. So, this is 1 and E s is 70 into 10 to the power 3. So, this value is 2286. So, as I mentioned, my C nu will be 1 because the Poisson ratio itself is 0.5. So, this is C nu which is equal to 1. Now, C k we have to calculate for corresponding to this k equal to 286. So, beta 0 we have calculated, this is 0.05, this is the value, and for k equal to 286 and L by D is equal to 30. So, this value will be C k value will be around 0.6. So, this is for 30 will be somewhere here and this is 286 will be here. So, this is the C k value. So, C k value or the beta 0 value is been calculated as 0.05 or is been taken as 0.05 from the curve, and C k value for correction factor due to pile stiffness, and that is equal to 0.6 because k is equal to 286, this is 286, L by D is equal to 30. So, this will be around 30, 25, this is 50, this is 25, 10, 5, 2. So, 30 will be around here. So, this is the value, that is 0.6. So, we can write that C k is equal to 0.6. So, finally, this beta is equal to beta 0 is 0.05, C k is 0.6, this is equal to 1. So, this value will be 0.03. So, now similarly, we have to calculate I value also, because in this expression there is a term I and beta, these two we have to calculate, and I have also discussed that what is I in the last class. So, that means is I is equal to given as I 0, R k, R h and R nu, and that is also for floating pile, and for end bearing pile there will be different corrections. End bearing pile there will be R b is there, similarly C b is there, but here it is a floating pile. So, we are not taking those R b or C b value. So, again this I 0 we have to calculate, and I 0 value we can calculate from the chart that I have given. So, anyhow here the I 0 chart, yes, this is the I 0 chart, because this is C k and C nu is for floating pile. Similarly, for your end bearing pile we have to introduce C b, but here it is not end bearing pile. So, that is why we are not taking the C b value. So, these are the C b charts for different L by D ratio and different E b by S also. E b is the elastic modulus of the base stratum or the ridge stratum, and then the elastic modulus of the soil above that ridge stratum. So, I 0 is for dB by B equal to 1, L by D is equal to 30. So, this is the value, and I 0 will be 0.064. So, here the I 0 value, this is 0.06, this is 0.07. So, and it is in log scale. So, this remember that this is in the log scale. So, that is it, that means I 0 is 0.064. Similarly, our R nu will be 1, again because Poisson ratio is equal to 1, and there is a term R h. R h is that if there is a ridge stratum and then within that soil, this is a floating pile. Pile is not resting on the stratum, but there is a ridge strata, and then the length of the pile is say L, and the thickness of that soil layer is H. In such case, we have to use the RH, okay, because this is a effect of finite soil layer. But our case any that type of information is not given, whether there is a finite soil layer existing or not. It is given a soil layer whose properties are given. So, that means we assume that there is no registratum is there. So, it will be a infinite, or the length of the soil layer is large enough. Okay. So, that we will not apply that correction. So, that means we will consider there is no finite strata. Okay. So, that means here that small h value is not a finite value. So, that means is the large depth. The depth is of this strata is relatively large. So, we can say in that case that our R nu will be equal to 1 and R h will be also equal to 1, because we are not incorporating the effect of finite strata. But there is a R k, and R k value is, your k value is 286. So, this is 286 and L by D is equal to 30. So, that will be again here. So, 286 and 30, this is the 30 curve say. So, 286, then this value will be around 1.6, this is 1.2, 0.4, 0.6. So, this is the value. Okay. So, this value is 1.6, okay, because this is 1.2, 1.4, 1.6, 1.82. So, we have determined these values. So, we will put these values here. So, that means the I 0 is 0.064, R k is equal to 1.6, R h is equal to 1 and R nu is also equal to 1. So, we can say that I value is equal to 0.064 into 1.6 into 1 into 1, and that is equal to 0.1024. Okay? Because this is a floating pile. So, this is the information are given. So, based on that we have determined these values. Now, we have to calculate these 4 quantities, and equations are given for these 4 quantities, and I have derived all these equations in the last class. So, directly I will use these equations or these 4 values. Okay. So, first one is P y 1 and that is equal to P s u divided by 1 minus B. So, we can calculate that P s u is the ultimate frictional resistance of the pile, and that we can calculate as A s alpha C u into L. Okay. That is the ultimate friction resistance of the pile. So, if we put this value, that A s will be the, this is A s. So, A s I have written. So, L is already incorporated in that A s. So, we can write that A s equal to pi d into L, pi d is equal to 0.5 and L is equal to 15. Okay. And the alpha value is 0.35, alpha is 0.35 and C u, average C u along the length of the pile or along the shaft of the pile is 100 kPa. So, this is the value. So, P s u is 825 kilonewton. So, ultimate friction resistance of the pile. Similarly, P b u, ultimate base resistance of the pile or the tip resistance of the pile, that is equal to 9 C u into A b. So, this is equal to 9 into C u is 100, C u b at the base is 120 into the area pi d square by 4, d is 0.5 square divided by 4. Okay. So, this is equal to 212. So, we know the ultimate friction resistance, we know the ultimate tip resistance also. So, PSU is 825, then 1 minus beta is equal to 0.03, okay. So, this is equal to 850 kilonewton. So, what does it mean that when the friction resistance is fully mobilized, that means 825 kilonewton, in that time the tip resistance contribution will be 850 minus 825, 25 kilonewton. Okay. So, that means here when the friction resistance is fully mobilized, that time also there will be some tip resistance, and that tip resistance here is 25 kilonewton. 825 is friction resistance, total is 850 kilonewton. So, tip resistance contribution is 850 kilonewton minus 825 kilonewton is equal to 25 kilonewton. Okay, so, now we will calculate what is the deformation at this is the load when the friction resistance is fully mobilized. So, at that point the deformation is equal to, that expression is also given, and this is the expression. So, that expression is given I ESD PSU 1 minus beta. So, we will write that. So, I ESD PSU 1 minus beta, or directly I can write I ESD into P y 1. Okay. So, I value is how much? I value is 0.1024. So, I value is 0.1024, ES is 70 into 10 to the power 3, then D is equal to 0.5 and P y 1 is 850. So, at that point settlement is 2.49 or roughly 2.5 millimeter. Okay. Now, we will calculate the ultimate settlement, because we know the tip resistance and the base resistance. So, total load carrying capacity of the pile is summation of the friction resistance and the base resistance. So, that will be 825 plus 212, that will be 1037 kilonewton. Okay. So, at that moment the ultimate settlement, that expression is also given, that is equal to I by ESD into PBU divided by beta, okay, plus PBU minus PSU 1 minus beta into beta, and that is into L divided by AP EP. So, now I will put these values. I is equal to 0.1024, ES is 70 into 10 to the power 3, diameter is 0.5, then PBU is 212, beta is 0.03, then plus PBU is 212 minus 825 is the PSU, PSU is 825 into beta is 0.03 divided by 1 minus 0.03. Then length of the pile is 15, then area of the pile is pi 0.5 square divided by 4, and EP is 20 into 10 to the power 6. EP is 20 into 10 to the power 6. So, from there I will get the value as 20.7 plus 0.71, that is 21.4 millimeter. So, from here you can say the soil deformation is 20.7 millimeter, and the deformation of the pile material is 0.71 millimeter. So, overall is 21.4 millimeter. So, finally, we know these all 4 values. So, finally, we have drawn this load settlement curve. Okay. So, this is the settlement and this is the load. So, you can see that from here that when the total load, when the friction resistance is fully mobilized is 850, settlement is 2.5. So, the total load is 850 and settlement is 2.5. Similarly, the total pile load carrying capacity, the tip resistance plus base resistance is 1037 and the total settlement is 21.4. So, 1037 total settlement is, this is 1037, this is 1037 and total settlement is 21.4. So, that means here this is 1037, or I should write that x coordinate is 21.4, 21.4 millimeter and 1037 kilonewton. Okay. And this is 2.5 millimeter and 850 kilonewton. Okay. So, similarly, I can draw the other 2 curves also. So, the other 2 curves if I draw the all curves like this one, then the values will be, so for when the friction resistance is fully mobilized. So, that time also this will be 2.5, but the value is 825. Okay. So, this is 850, this will be the value around something like this. So, 825 is the values. Okay. So, I can draw, this is the curve, because there is only slight extra value due to the tip resistance, and this is also 2.5. This curve is also, this is also 2.5. Okay. So, I should draw like this. Okay. So, and then it will be parallel to x axis. Okay. So, this is the shaft load settlement curve. Okay. So, and in this condition the tip resistance is only 25 at this settlement, only 25, this is the tip resistance you can say, and that will continue like this up to this value, and total tip resistance is 221. So, 221 means to a 212, 212 will be somewhere here. Okay. So, I can draw, this is like this. Okay. And then I can extend that. Okay. So, now this is the curve for base load and settlement. Fine. And then I have discussed that there will be a portion that is due to the pile material settlement, and that value is less than 1 millimeter. So, I can draw something here. So, this will be here. So, I can extend the draw that curve also, but the difference will be very small as the deformation is only 0.71 millimeter. So, which is less than 1 millimeter. So, if I write those values, so this coordinate, the value will be 2.5 millimeter and the y axis load will be 825 kilonewton. This coordinate, the values will be again 21.4 millimeter and this is 212 kilonewton. Okay. So, and this will be this additional deformation due to the pile material is 0.71 millimeter. Okay. So, this is the curve. So, I can draw the overall curve like this. So, this will add and then it will be parallel to this base settlement curve. So, this one is the overall curve, this is the overall load versus settlement. This one is the shaft load versus settlement, this is the base load versus settlement, and this one is the additional settlement due to the pile material deformation or pile deformation. So, this way we can determine the load settlement curve theoretically for a pile and with definitely with some assumptions, and that I have discussed mentioned previous class. So, here I should say that actual deformation or the load versus deformation curve may be the nonlinear in pattern. So, but here it is represented into linear curves or in linear form. So, which is almost closely will get the actual behavior, because maybe actual behavior there will be points will be around this curve. Okay. So, this may be the actual behavior. So, which is not exactly this bilinear type of deformation pattern, but by this bilinear type of deformation pattern or simplified approach, we can approximately obtain the load settlement curve of a pile by using theoretical approach. Okay. So, in the next class I will discuss the next topics related to the piles, for example, the other different ways by which we can determine the load carrying capacity of the pile, and then I will discuss how we can calculate the consolidation settlement for a group pile and how we can determine the group efficiency for the pile. Thank you.